SANY Demonstration Fusion Web Processing Service. This video comes in 3 sections. We'll first introduce the architecture used throughout the demonstration, and then show you the setup, fusion and storage phases of a typical case study fusion job. The fusion architecture used throughout this demonstration comes from a variety of components built by the partners within the SANY project. From IT Innovation, we have a web processing service which hosts a variety of fusion algorithms, for example kriging. This web processing service has as input data access to a number of sensor observation services where the sensor measurements are stored ready for use. To provide a user interface, we have a web page SSE client coupled with a map and diagram service for easy display and running of fusion jobs. We also make use of Google Earth visualizations, which are automatically created by the web processing service. The workflow involved in running the web processing service consists of an offline and online phase. The offline phase involves drawing polygons to indicate areas of spatial cohesion that experts have identified. These are then segmented and used as input to the kriging algorithm. The online phase involves downloading data from a sensor observation service, which is selected on demand, and also downloading regions which were previously created from an FTP site. The web processing service is then executed, kriging is run, and the results downloaded to both an FTP site and a separate Fusion SOS for long-term storage. The results can be visualized using the Google Earth representations as part of the KML formatted output. Setup phase. Identification of regions of spatial cohesion. As can be seen, the user has opened up a Google Earth session and is drawing some polygons on top of buildings to indicate areas of spatial cohesion. These polygons can consist of several points connected together to produce a closed filled polygon. In this example, we will draw polygons around a lot of the buildings within the area of interest that we want to do our spatial interpolation. This provides the kriging algorithm with a clear indication of which areas will be spatially coherent, and this will improve the final output of the interpolation results. For ground displacement, buildings make sense, but for other phenomena such as wind, you might want to identify coastline and areas where there is rough terrain. In our ground displacement use case, you can see that we have a number of sensors indicated by the yellow pins which are attached to buildings to provide ground displacement measurements over a period of time. Our final polygon set closely matches the buildings where the sensors are located. Once finished, we can save our Google Earth polygons as a KML file, and this can then be loaded in to the region segmentation process for automatic region segmentation and the identification of the final region set. Now, switching to the SSE web page, which provides an interface for our web processing service, we can select the region segmentation service to read in our Google Earth polygons, the KML file, and segment them. In order for our remote service to access the KML file, we need to store it on an FTP site and provide the URL via the SSE portal interface. As can be seen, the FTP site is available and the KML file has been uploaded. We will now copy the URL and paste it into the SSE portal interface so that the web processing service knows which URL to download for the KML file. Back with the SSE portal, we'll now fill out the remaining configuration. We specify the resolution of the grid that we want to segment over and the pixel blur, which is an indication of how segments should blur into each other and how hard the individual boundaries are. In addition to the resolution, we need to specify the exact bounds of the spatial region that we wish to segment over. This will be an area in Barcelona which covers the Google Earth polygons which we've just drawn. Now the spatial bound has been identified, we will run the kriging service by clicking the search button, and this will start the process running. We can get regular status updates by clicking the refresh status page until the job is finished. Now that the process is finished, we'll see that there are three outputs. We have two CSV files, which are maps of points and region IDs, and we have a KML visualization, which is a courtesy visualization to show the user what the segmentation map looks like. Okay, back with Google Earth, we can now load in the visualization of the segment map. There we go. And you can see that each of the buildings, which were identified with polygons, now have a different colour, which indicates a region ID. We can also, within Google Earth, load the original polygons back in, so you can see how closely the segment map corresponds to the original polygon map. This data is now available for running the live runtime web processing service and will help the kriging algorithm produce better variograms for each of its regions. Fusion phase, kriging. Okay, back with the SSE portal interface to the web processing service, we'll now select the kriging process and start a kriging run. The first thing to do is to select the dataset. This is done on demand, and the user can select any dataset from a set of profiles. The second parameter is the CSV file location of the segment map, which we find on the FTP site again. Since we are measuring ground displacement, we need to enter two time values from which the sensor measurements will be determined. These values will be 4 months apart, and the system will calculate the delta between the two. We can also specify a sampling window, measured in seconds, from which the latest value of any particular sensor measurement will be taken. This is useful if sensors do not all report at the same time. We specify an observed property of the Z motion, which is the ground displacement along the Z axis. And we'll specify a grid resolution for our interpolation grid of 20 by 20. Finally, we need to specify the interregional correlation factor. For buildings, this will be 0, since one building does not impact much on another. For wind properties, for example, we might want to have a higher factor, since the wind measurements in one region can quite heavily impact the measurements on another. As for the regional segmentation, we need to specify a kriging interpolation area by drawing a bounding box. We'll do this again using the bounding box for the Barcelona region. As before, we'll click the Start button to initiate the process, and this starts the kriging running on the remote server. The sensor observation service is queried, the sensor measurements downloaded, and the kriging performed as per the configuration. Once finished, we can see that the kriging has generated a number of outputs. We have CSV data for the raw data files, and this contains the values which can be loaded into applications such as MATLAB or Excel. We also have KML files for visualizations, and we have a number of XML files which are formatted according to the OGC SWI standard set. Files are available, as before, on the FTP site, and the observation and measurement files are also uploaded to the Fusion SOS for longer term storage. Back with Google Earth, we can now look at some of the results. Here we have the spatial interpolation for the Barcelona region. You can see that the values are negative, so the green graph is going down rather than up. We can scroll around and bring in a heat map which gives us the error values associated with the interpolation estimates. The darker the red, the higher the kriging variance. To demonstrate our dataset plug-and-play capability, we've done exactly the same kriging run, but this time on some wind measurements in the Gdansk area. You can see by the yellow pins that we have 14 wind sensors, and we've krigged over the area. The arrow map shows the wind speed and wind direction. The strength of the wind is indicated by the colour, and the direction of the wind is indicated by the direction of the arrow. All the other maps are also available, so we have the heat map for kriging variance and the green graph for wind speed. For our third and final dataset, we'll run the same kriging, this time on the UK Met Office wind data. You can see the same results are available, this time for the south of England. The green graph is the wind speed, and the heat map is the kriging variance. As can be seen, we have 3 different datasets hosted by sensor observation services. They have 2 different data domains, wind and ground displacement, and these can be processed using a single generic algorithm. Storage phase. After our previous Fusion run using the Web Processing Service, our results are now stored within a Fusion SOS. So we have here the SSE Portal web client to the Fusion SOS, which we'll use to extract our results. This time, instead of specifying the sample time of the sensor measurements, we'll specify the result time when the results were computed. Providing the process ID allows us to track down the exact results, which we can then display using the SSE Portal window. As before, the search button starts the process, and the results are returned and displayed in both the Map and Diagram Service window and below the individual results for the observations. Since we are using a Fusion SOS to store our results, the results come out looking like a normal sensor observation service. So we have a time window when the results are valid, and we have a spatial region, in our case a grid, where the points are covering. You can see on the Map and Diagram Service that the blue rectangle indicates the spatial interpolation grid that we ran for the Gdansk run. Scrolling down, you can see that the results are also available in a tabulated form, allowing users to look at the specific values. For linear sequences of values, for example temporal plots, we can bring up a graph. This is particularly useful at looking at values which vary over time. Summary. As you can see, within SANY we have developed a fusion capability based around a web processing service that is fully OGC standard compliant. We extract data from sensor observation services and run our processing services using the WPS. Our generic fusion approach separates the data and configuration from the algorithm itself, allowing reuse of algorithms on many different datasets. And our use of OGC metadata to automate the pre-processing of datasets realizes our plug-and-play sensor measurement capability. The challenges that we see ahead are based around very large datasets, handling massive data in an efficient and targeted manner, and about processing real-time information feeds such as camera and streaming information. This, coupled with our approaches to combine expert knowledge with the algorithmic processing, is where we see the future challenges ahead of us.